There hasn't been a big earthquake on the southern San Andreas Fault for a long time, and we may have found a reason why.
Beneath the surface of California lies a giant waiting to awaken. The San Andreas Fault, a name synonymous with destruction and fear, has long been a sword of Damocles over the head of the Golden State. It is always closely monitored, but recent discoveries indicate that something even more catastrophic is on the horizon. The question is, when will the San Andreas Fault finally give way? Join us as we delve into the latest findings at the San Andreas Fault, unraveling the mysteries that terrify not just Californians, but the entire world. The kind of movement along the fault. The San Andreas Fault is a name that immediately triggers thoughts of catastrophic earthquakes, especially for those living in California. It is a significant crack in North America's far western part of the Earth's surface. This fault stretches for over 800 miles, running northwestward from the northern end of the Gulf of California, through the part of the west of California, and then reaching the Pacific Ocean in the region of San Francisco. What makes this fault so feared is the constant tectonic movement detected around its base, often leading to earthquakes along its path. A tragic example that still resonates with Americans is the destructive earthquake that struck in 1906. Although a minor quake happened in 1989, 5 years later, the suburbs of Los Angeles experienced a more powerful and damaging earthquake along one of the San Andreas's more considerable secondary faults. During the 1906 earthquake in the San Francisco area, roads, fences, and rows of trees and plants that spanned the fault were shifted many yards, with the road at the head of Tamales Bay being moved about 21 feet, the highest offset recorded. In each case, the terrain west of the fault shifted substantially northward. The sudden offset that causes a big earthquake happens on only one portion of the fault at a time. Total offset increases unevenly over time, typically due to movement on one fault segment followed by another. The portions that create massive earthquakes stay locked and calm for 100 or more years as tension builds up. Suddenly, the strain is released in enormous lurches, causing great earthquakes. However, other stretches of the fault apparently accommodate movement more by constant creep than by sudden offsets that generate great earthquakes. Geologists think that since the San Andreas Fault formed around 15–20 million years ago, there have been at least 350 miles of displacement due to earthquakes and creep. Studies on a portion of the fault between Tejon Pass and the Salton Sea found geologically identical terrains on opposing sides, now separated by 150 miles, and some crustal blocks may have shifted more than 20 degrees latitude. Although it is difficult to fathom such significant shifts in the Earth's crust, the pace reflected by these ancient offsets is consistent with the rate recorded over time. Surveys reveal a drift rate of up to 2 inches each year. The hopes to a potential earthquake disaster. Despite the devastation caused by these events, it's important to note that the fault line did not move directly through the affected towns. However, several communities lie squarely on the fault line and are vulnerable to a potential earthquake disaster. Point Reyes Station, Fraser Park, Daly City, Desert Hot Springs, Gorman, San Bernardino, Wrightwood, Palmdale, and Bodega Bay are all sitting ducks. The recent announcement by Thomas Jordan, the director of the Southern California Earthquake Center, about the critical state of the San Andreas Fault has turned the minds of every Californian and made them anxious. Thomas says the fault line is critical, and a massive earthquake could loom underneath. The Californian residents are already living with the fear that the fault line could unleash at any moment, but this new warning has made them even more scared. The Southern California section of the fault line is particularly vulnerable, and Thomas commented that it looks like it's locked, loaded, and ready to go. The last time this region suffered such a disaster was in 1857, when a magnitude 7.9 earthquake ruptured a breathtaking 185 miles between Monterey County and the San Gabriel Mountains near Los Angeles. It has been too quiet for too long, and the springs on the San Andreas system have been wound very tight. The recent announcement made during the National Earthquake Conference in Long Beach has put everyone on high alert, and they are now wondering when the next earthquake will hit and how devastating it will be. What is an earthquake? Stresses from deep inside the Earth distort the Earth's crustal plates. The ground bends first, then breaks and snaps into a new position when it reaches a particular limit. During cracking or faulting, vibrations that cause earthquakes are created. Some vibrations have shallow frequencies, with many seconds between waves, while others are high enough to be audible. Vibrations are classified into two types: compression and transverse or shear waves. Because compression waves move quicker through the Earth, they reach first at a remote location, known as primary or P waves. The transverse waves that arrive later are known as shear or S waves. In an earthquake, humans may initially notice a firm thud or blast-like jolt, which signals the entrance of the P wave. A few seconds later, individuals may experience a swaying or rolling motion, indicating the advent of the S wave. Intensity is a measure of the strength of shaking during an earthquake. The modified Mercalli scale depicts an earthquake's local effect or damage. The intensity recorded at various sites tends to decrease farther from the earthquake epicenter. The intensity range is given in Roman numerals, from I to 14. For example, persons in favorable positions would scarcely feel an earthquake of strength 2, whereas intensity X would cause heavy damage, especially to unreinforced masonry. Local geologic conditions strongly influence the intensity of an earthquake. Commonly, sites on soft ground or alluvium have intensities 2 to 3 units higher than sites on bedrock. The formation. The San Andreas began to form in the mid-Cenozoic about 30 million years ago. At this time, a spreading center between the Pacific Plate and the Farallon Plate, which is now mostly subducted, with remnants including the Juan de Fuca Plate, Rivera Plate, Cocos Plate, and the Nazca Plate, was beginning to reach the subduction zone off the western coast of North America. As the relative motion between the Pacific and North American plates differed from the relative motion between the Farallon and North American plates, the spreading ridge began to be subducted, creating a new relative motion and a new style of deformation along the plate boundaries. These geological features are chiefly seen along the San Andreas Fault. It also includes a possible driver for the deformation of the basin and range, separation of the Baja California Peninsula, and rotation of the transverse ranges. The main southern section of the San Andreas Fault proper has only existed for about 5 million years. The first known incarnation of the southern part of the fault was the Clemens-Well-Fenner-San Francisquito Fault Zone, around 2213 MA. This system added the San Gabriel Fault as a primary focus of movement between 10-5 MA. It is believed that the modern San Andreas will eventually transfer its motion toward a fault within the Eastern California shear zone. This complicated evolution, especially along the southern segment, is mainly caused by either the Big Bend or a difference in the motion vector between the plates and the trend of the fault and its surrounding branches. Earthquakes along the fault. Every year, dozens of minor earthquakes occur throughout California, giving geologists a good idea of where faults fracture the Earth's crust. The most significant historical earthquakes along the San Andreas Fault occurred in 1857 and 1906. The disaster in Southern California on January 9, 1857, severe damage. It was very similar to 1906 earthquake in San Francisco. The movement of the Earth itself, as reported by the press, is indicated by an almost identical symbol in both incidental cases. The reported write-up of the 1857 earthquake illustrated that the fault changed a loop shape of the sheephold to a S shape that was a characteristic of left lateral strike slip. Studies of offset stream courses show that up to 29 feet of migration occurred in 1857. The disastrous giving of an earth move and fire on April 18, 1906, due to San Francisco, had resulted in over 700 deaths and millions of dollars in damage to the state of California, from Eureka to Salinas, and more further. Across distinguished places, including Oregon and Central California, Nevada, destruction and damage extended widely. The 1906 San Francisco earthquake, approximately determined being 8.3 in magnitude in Richter scale, produced modified Mercalli scale intensities of up to Haguentour. Surface offsets occurred along the fault's 250-mile length, from San Juan Bautista north to Point Arena and offshore to Cape Mendocino. On May 18, 1940, a 7.1 magnitude earthquake struck the Imperial Valley along a previously unknown fault. A similar displacement along the Imperial Fault happened following an earthquake in November 1979. The 1940 earthquake produced the most surface displacement, 17 feet of right lateral strike slip. This fault is a component of the San Andreas system. All in all, there were several earthquakes of likely magnitude 7 or higher, which took place on the Hayward Fault from 1836 to 1868 and on the San Andreas Fault as well, from 1838. The San Andreas Fault have since been the source of worries for the Californians, and there was every reasons for those. It is an important interplate boundary that yields the Pacific Plate being subtly spliced northwestwards, vis-a-vis the North American Plate. This action should relieve around 16 feet of cumulative plate movement per 100 years, but the tension has accumulated for over a century. The Southern California Earthquake Center director, Thomas Jordan, recently said the fault is critical and a great earthquake could be looming. However, this section of the San Andreas Fault is one of many overdue for an earthquake. San Bernardino County, around the southeast in the Tejon Pass, has not significantly moved since an earthquake in 1812. But some omissions from the southeast region towards Salton Sea between 1680 and 1690 are recorded. A more complex point is that geologists are researching the columns of tectonic plates' motion northwestward movement of the Pacific Plate roughly 10 millimeters per year and north of the North American Plate. Jordan advises the California government to focus on preparing for a potentially powerful earthquake as brutal as a magnitude 8. He praised Los Angeles for taking proactive measures to mitigate its earthquake vulnerability by incorporating earthquake retrofits into apartment and concrete buildings. It is critical for other communities, like those in San Bernardino County, to follow suit and take the necessary steps to become vital in the face of an impending earthquake. Is California prepared? Mayor Eric Garcetti of the LA is amongst the city officials who have been working persistently to protect Los Angeles from the worst case, which is an earthquake. Thomas Junderson, the director of the Southern California Earthquake Center, is happy to have Omar Rich, who now promotes earthquake repairs on apartments' concrete buildings. Jordan expressed his surprise at the success of this plan and said, "It's remarkable that this happened. We know politically how difficult it is to make these changes. However, despite these efforts, California must still prepare for what will come." With San Andreas's fault finally giving way, the state faces one of the most devastating natural disasters ever. According to a report from the U.S. Geological Survey, a magnitude 7.8 earthquake on the southern San Andreas Fault could cause 50,000 injuries, $200 billion in damage, and severe, long-lasting disruptions. This powerful earthquake could last almost 2 minutes, with the most vigorous shaking happening in areas like the Coachella Valley, Inland Empire, and Antelope Valley. It could also result in pockets of vigorous shaking in areas where sediments trap shaking waves, such as the San Gabriel Valley and East Los Angeles. Extra to this, the sewer system might not be available after 6 months, and it is foreseen that as many as 1,500 perish. This grim scenario definitely calls for awareness and measures to perpetuate even beyond the worst. In addition to fortifying the municipal water system and the telecommunications faulty networks, other issues featured in this policy are protecting the public from power lines and other enhanced measures implemented during a disaster. A quick response from response agencies in California is a must in order to reduce the impact and save lives that could be lost in a major disaster as such. If a major catastrophe happens because of a rupture of the San Andreas Fault, or if case would be a historical example that resembles Fort Tejon quake in 1857, can be easily understood by monitoring all these adverse effects. This earthquake, estimated to be 7.9 magnitude, was so powerful that it earned its name despite starting farther north in Monterey County and moving southward through Fort Tejon to the Tejon Pass in San Bernardino County. The shaking lasted 1 to 3 minutes, causing soil liquefaction and uprooting trees in places as far as Stockton. However, even though the San Andreas Fault runs directly into Los Angeles, it is located 30 miles from downtown. Unfortunately, this distance doesn't mean the city is out of danger. The city is counted to have very terrible aftershocks as a large earthquake closer to the San Andreas Fault occurs. The answer to the question of the extent of the damage to be was revealed by the Jordan team. They recreated a 7.8 magnitude quake on the fault. The simulation starts from the Salton Sea and moves west toward the San Gabriel Mountains, showing how seismic waves can affect the Los Angeles area. Additionally, another simulation video shows the shaking of the ground stretching from northern San Diego County to Barstow. In 2010, the Southern California Earthquake Center used a supercomputer to create a simulation of what a magnitude 8 earthquake on the San Andreas Fault would look like. The simulation was designed to be similar to the powerful 1857 earthquake, but even stronger. It begins in Monterey County and moves further south towards the Mexican border, with the LA Basin and San Fernando Valley hit hard due to the trapping of shaking in soft soils. You can see that this area of influence by the shaking has expanded to huge proportions, says Jordan. The directivity pulse shoves energy down the fault and excites sedimentary basins like the San Fernando Valley, Los Angeles Basin, and San Bernardino. The shaking in the Los Angeles region would persist for long periods. If the simulation were to happen, what type of fault would we call the San Andreas, the line dividing two major faults on the upper crust of the Earth? According to the theory of plate tectonics, the San Andreas Fault is the boundary between two major plates of the Earth's crust. Based on the theory of plate tectonics, it is explained that the San Andreas Fault is created as a border between two significant pieces of the Earth's crust, the Northern Pacific to the south and west, and the North American to the north and east. The Northern Pacific Plate is moving laterally past the North American Plate in a northerly direction, making the San Andreas Fault a strike-slip fault. Though the plate movement relative to each other has been about 1 centimeter per year of geologic time, the annual activity rate has been 4 to 6 centimeters per year since the early 20th century. Because natural disturbance occurs in this kind of event, there will be time before the occurrence of the future one. The 6.4-meter shift of some portions of the San Andreas Fault is notable as it caused catastrophic tremors, even in the 1906 quake. There is also a chance that some, though few, might still call the San Andreas Fault a transform fault. But getting a grasp of what that means can be tricky too. Try visualizing 2 slices of pizza on a table, one with pepperoni toppings, and the second with anchovies as toppings. A stream of firings and a sputtering comes through as the sides run into each other, and pieces of pepperoni crack and fall on the anchovy side. This is what exactly takes place with the fault, which has made a deep hole large enough to accommodate the oceans, making the biogeography and the landforms along the rift very complex and unpredictable. The fact that it gets the movement slow should be remembered with an average speed of likes per year when you look at how your fingernails are growing. While this movement is not even, and plates are often stuck on each other, they fight to move without remainder. In such a way, the motion is just a few inches yearly. It may take a long time for the strain to accumulate and reach a level of breaking the rock along the fault. However, once the rock explodes, the slipping of the plates may be accompanied by a sudden movement of up to several feet, generating small waves that instantly propagate away from the earthquake center as the surface shakes. The San Andreas Fault is not only about the 120-mile-long line of land, but is still a driving force behind many Californian residents' lives. Even more impressive is that several California areas have little pieces of this phenomenon. If you take a trip to the Carrizo Plain, located in San Luis Obispo County, you can get a glimpse of this mighty fault. It's also visible in Marin County, where the fault's signature scarps and pressure ridges can be observed. However, not all parts of the fault are as easy to spot, as some are covered in brush and alluvium or haven't moved in many years. In urban areas like Los Angeles and San Bernardino, roads cut through towering mountains of gouge, powdery, crushed rock pulverized by the moving plates. But the San Andreas Fault is more than just a physical entity. It's a geological masterpiece that spans over 30 million years. The location. As the plates moved and collided, rocks from vastly different regions were forced together, creating a diverse array of rock types on both sides of the fault. We can say that the Southern California gray wacka bedrock near central Northern California originated from Southern California. This volcano, the Neenach volcanoes in Los Angeles County, and the other half of the volcanic system that begins 200 miles southeast in Monterey County, make up the total volcano. While some may object that the San Andreas Fault caused the earthquake, the truth is that the tectonic power will always be the monster that not many can comprehend. Legend is attached to the San Andreas Fault, from which many tales and fake stories have been created throughout history. The fact that the fault can occasionally produce massive earthquakes cannot be considered a myth, a gross exaggeration. The idea that it can cause a megathrust of magnitude 10 or more is. Studies have determined that during the historical record, such big earthquakes never happened in the asthenosphere. They only happened on the surface, where larger faults are visible. The large-scale subduction model would work only if the San Andreas Fault would be as long as the fault that causes the quake of this magnitude, 880 miles, at least 2 or 3 times. However, it is noteworthy that the formal value is directly linked to the fault length at which an earthquake occurs. Besides that, the San Andreas Fault will rarely cause earthquakes, but it is not 100% sure. Therefore, a major quake is still possible in the San Francisco Bay and Southern California. Scientists estimate a 60% chance that a sizable earthquake will occur within the next 30 years, localized in the above-mentioned areas. Enough to be conscious of the threats lying in wait and implement all the rules that ought to be regarding your safe ear partner. Beyond these doubts about the San Andreas Fault, scientists have still advanced some ideas on how the geoscientific phenomenon of ground movement can be predicted in case of an earthquake. This information works with engineers and code developers of the building standard organizations to ensure the safety of the structures and can withstand earthquakes. 1857, Fort Tejon. Although the San Andreas Fault has no glory, it is known to produce some of the most destructive earthquakes the world has ever witnessed. Whereas residents are familiar with past strong quakes, such as the Fort Tejon earthquake in 1857 and the 1906 San Francisco earthquake, the big question on everyone's mind now is if the next one will be as destructive as the others. Through San Francisco, with all its vivid remembrance of the destruction it brought after the downtown buildings and the death of tens of thousands of people. Conversely, the other earthquake that was the most nearing was the Great Fort Tejon earthquake. This one was felt all over the territory. Intriguingly, Fort Tejon was not at the point of the earthquake, and the traceback was to the earthquake's epicenter in Parkfield in Monterey County. The throw started from Parkfield's northwest and appeared southeastward of the San Andreas Fault for just over 360 kilometers. The quake hurled Fort Tejon right in the middle of the break, and the tragedy inflicted much larger damage than other scanty populated areas in South California. The 1857 Chiquita Fort earthquake was bigger than the 1872 Owens Valley earthquake. It had nearly the same force, if not larger, compared to the 1906 earthquake in San Francisco. Scientists are unable to forecast earthquakes as they would other phenomena. Moreover, they continue to analyze the fault and gather information about its behavior, which will aid them in dealing with the earthquake's power. The 1857 Fort Tejon earthquake was one of the most powerful, estimated to be at the magnitude level of 8.0, as it occurred close to the fault, increasing its devastating effects. The 1906 predominant earthquake caused an estimated $5 million damage inflicted on the northern segment of the fault. Yet the longer shaking experienced during the 1857 and 1906 quakes, which lasted for up to 2 minutes, dictates a high likelihood of destruction extent during an imminent earthquake shortly. It is interesting to note that areas like Los Angeles, San Bernardino, and Santa Barbara, not close to the fault line, were shockingly avoided by the destruction during the 1857 earthquake. In contrast, Fort Tejon was battered by aftershocks for months and even years after the main shock due to its proximity to the fault. By estimating that if the given cities, such as Wrightwood or Palmdale or those in Fraser Park and Taft, were around in that area at the time, they would have most likely felt the intensity of the quake to a similar level to that of the people who were at Fort Tejon. The next big one is purely a question of the time interval and not the length itself. Interestingly enough, scientists are yet to figure out either. It will happen or it will be as big. While natural disasters bring in uncertainties, it's mandatory for the Southern Californians to be vigilant and ready at the moment of the earthquake, as they can be unprecedented. The next great jolt of earthquake on San Andreas. Of course, along fault zones, from the San Andreas to the regions which haven't had major quakes for decades, you would find little activity. Scientists refer to these segments as seismic gaps and have generally been effective in predicting when some seismic gaps would cause big earthquakes. According to geological research, significant earthquakes on the southern San Andreas Fault have occurred at around 150-year intervals over the last 1,400 to 1,500 years. Because the previous considerable earthquake in the south of San Andreas occurred in 1857, that area of the fault is considered a plausible candidate for an earthquake in the following decades. The San Francisco Bay region has a little lesser possibility for a great earthquake, as less than 100 years have passed since the great 1906 earthquake. However, the area around can experience the impact of small and moderate-scale earthquake with strong damage on the population even during a calm time. Earthquakes are generally not precise in striking unless warned, and hence it is often extremely hard to predict when an earthquake is going to occur. Such rupture has a higher chance of being preceded by increased seismic activity during a prolonged period of several years that is always accompanied by frequent small earthquakes, the size of magnitude 5 on the fault. Seismologists expect to notice changes in the Earth's surface before the next significant earthquake, such as shorter survey lines across the fault, elevation changes, and repercussions on strain meters in wells. Research focusing on the prediction of earthquakes gains a lot of validity from the discovery at Parkfield, California, close to center of country, of a short section of the San Andreas Fault, prone to record an average of a quake small to moderate size every 20-22 years during last 100 years. During the last significant earthquake, which was recorded in 1966, the town of Parkfield became a very appropriate area for the magnitude 5.6 earthquake to happen. And if the researchers take into account 1988 as their starting point, one earthquake may occur sooner than the end of the century, and this period of time may well be within a few years. The study shows that, as noted by a 2006 article in Nature by Yuri Israelich Fialko, an associate professor at the Scripps Institution of Oceanography's Green Institute of Geophysics and Planetary Physics, the San Andreas Fault has reached the pressure required for the earthquake of moment magnitude scale higher than 7. This finding also established that the possibility of having a big quake is now growing at a faster rate than what was predicted by the experts before. Additionally, these days, the potential hazard has been limited to the southern part of the fault, which includes the region around Los Angeles, because it is less than 300 years ago that the earthquakes took place on the central, 1857, and northern sector, 1906, of the fault, thus making the southern segment not active for the last 300 years. As a result of this analysis, it became clear that the powerful earthquake on the section of San Andreas Fault located in the south of region will cause major geographic and economic damage to the Palm Springs, Indio metropolitan area, as well as the other communities in the counties of San Bernardino, Riverside, and Imperial in California and Mexicali municipality in the Baja California. The consequences of an earthquake like this could be catastrophic and, perhaps, would inflict extensive damage on the area south of Los Angeles, which is heavily populated. Nonetheless, no significant earthquakes have occurred in the Los Angeles area in the 17 years since that publication, and two significant assessments produced by the United States Geological Survey, USGS, have made varying projections about the danger of future seismic occurrences. The capacity to forecast big earthquakes with enough accuracy to warrant heightened safeguards has proven elusive. Cascadia connection. U.S. Route 395 is a geological masterclass masquerading as a route. It stretches north from Los Angeles's arid fringes to Reno along the Sierra Nevada's eastern edge. Along the route, they pass the black cinder cones of Coso Volcanic Field and the worn marks of a powerful 19th century earthquake near Lone Pine. In the winter, vehicles may notice steam rising from Hot Creek as water boils from an active supervolcano deep underneath. Mono Lake appears around an hour from Nevada's border, with its bulbous and bizarre mineral structures known as tufa towers. Even if you're not interested in rocks, these are compelling, unearthly vistas. However, for James Faulds, Nevada's state geologist, they are something more. Clues to a tremendous tectonic mystery unfolding in the American West. If he's right, all of this, from the wastes of the Mojave Desert to the night-lit casinos of Reno, will someday be beachfront property. For almost a century, the San Andreas Fault has been regarded as the uncontested heavyweight champion of large-scale deformation in the West. The North American and Pacific plates collide, striving for a position with frequently severe consequences. According to the notion, the narrow sliver of land between the fault and the ocean, from the southern point of the Baja Peninsula to the Santa Cruz Mountains, will eventually break off from the mainland and move north, passing Los Angeles and San Francisco. However, there is at least one issue with this situation. The San Andreas looks to have become blocked. Northwest of Los Angeles, near the community of Fraser Park, the fault has kinked out of alignment so significantly that many geologists fear the pent-up tectonic force will have to seek release somewhere else. A 2008 report investigating previous earthquakes in the Pacific coastal zone discovered a temporal association between seismic occurrences on the northern San Andreas Fault and the southern section of the Cascadia subduction zone, which extends from Vancouver Island to the north of California. Scientists estimate that quakes in the Cascadia subduction zone may have caused most of the significant quakes in the northern San Andreas over the last 3,000 years. In addition, the data reveals that the rupture orientation in each of these time-correlated episodes is from north to south. However, the 1906 San Francisco earthquake is an exception to this association because the plate movement was mainly from south to north and was not preceded by a big quake in the Cascadia region, the future of Los Angeles, San Bernardino, and Santa Barbara. Although Los Angeles was not hit as hard during the last earthquake, it's still being determined how well modern structures would hold up in another big quake. Interestingly, local faults, such as blind thrust faults, pose a greater risk to population centers like Los Angeles, San Bernardino, and Santa Barbara, as they are closer to these areas and are less understood than the San Andreas Fault. However, San Andreas remains the biggest threat to places along the San Andreas Fault, like Fort Tejon and Palmdale. While earthquakes are the most commonly associated natural disaster with the San Andreas Fault, they can also cause severe flooding in certain areas. When the fault ruptures, it can create dams in rivers and streams, which may cause the water to build up and flood nearby areas. Additionally, the shaking from an earthquake can cause landslides, which can also dam up rivers and create floods. In some cases, large earthquakes on the San Andreas Fault have caused significant flooding in nearby regions. For example, the 1906 San Francisco earthquake caused widespread flooding in the city due to ruptured water mains and compromised levees. So, while the San Andreas Fault is primarily known for its earthquake activity, it is essential also to be aware of the potential for flooding. Continued monitoring and research are necessary to comprehend and mitigate the seismic hazard in Southern California. While we cannot prevent earthquakes, knowing the potential dangers can help us prepare and minimize their impact. Nonetheless, Californians and visitors must be prepared and informed on the latest safety measures. So, whether it's a family outing to one of the state or national parks strung along the fault, or simply driving down one of the peaceful, uncrowded roads that stretch alongside it, one thing is for sure: the San Andreas Fault remains a marvel and a mystery. The Southern California Earthquake Center has predicted the potential damage the San Andreas Fault could cause. However, there is always the possibility that the actual damage could be more or less severe than what was predicted. It is also still being determined whether the fault will remain dormant forever or when the next big earthquake will occur. What can be done about the faults and earthquakes? People cannot prevent earthquakes, but may learn to cope with the consequences. 3 primary lines of protection against seismic dangers are under development. Buildings in earthquake-prone zones should be designed and built to withstand earthquake shaking. Building rules that demand attention to earthquake shaking have improved in recent decades and serve as a first line of defense. In certain places, ongoing projects are being undertaken to fortify or demolish older structures more vulnerable to collapse during earthquakes. A second line of defense is the strategic use of land to mitigate the consequences of hazardous terrain. High occupancy or vital structures, for example, should not be located along the San Andreas Fault or in landslide-prone zones. The third line of protection will be accurate earthquake predictions. When such prediction becomes practicable, it will allow for the prompt evacuation of the most risky structures. Following the Earthquake Danger Reduction Act of 1977, the United States Geological Survey, other federal agencies, universities, and private companies launched a massive initiative to learn how to anticipate earthquakes and analyze and mitigate their dangers. What do you think about earthquakes and their dangers? Share your thoughts in the comments section below.